This contribution is from our colleagues from the Center of Mechatronics and Automation from Saarbrücken in Germany. The authors are Müller, Leenhard Hörauf, Matthias Vette-Steinkamp, Kanso, Julian, Koch. The paper is entitled The Assist by X System, Calibration and Application of a Modular Production Equipment for Visual Assistance. We are looking for your video presentation.
Hello, I am Kanso. Welcome to my presentation with title The Assistant by X System, Calibration and Application of Modular Production Equipment for Visual Assistance. The Assist by X ABX system is an implementation of a modular assistance system combining the advantages of modular engineering, mathematical modeling, and calibration, as well as easily programmable cyber physical systems communicating with their environment via MQTT. The idea for this project is to create a modular system that provides visual assistance for workers which can be adapted to different production environments with individual assistance tasks. In an assembly system, it represents an assistance model whereby the skills of the model can be defined by exchanging the projection device. For this reason, the system is called ABX, since the X is a representative for the different devices that can be implemented. So far, a laser projector, a moving head spot, and a smart video projector are implemented. Depending on the use case, it is expected to decrease processing time, probability of errors, or create a safer working environment on the production line, thereby increase worker performance. To not exceed the frame of this paper, the focus is placed on the ABX configuration with the moving head spot as a projection device. This has the following reasons. The moving head is a device usually used as theater and event technology and consequently does not have a standard calibration method which can be executed by a production worker rather than a light technician. Moreover, the moving head is not a cyber-physical system and cannot communicate with its environment, whereby it has to be equipped with a Raspberry Pi to meet the demands of an IoT scenario. The processing of the MQTT message into the device-specific commands is realized with the help of a Node-RED flow and is carried out with the other devices in a comparable way. The moving head has an open serial kinematic, therefore the kinematic and modeling problem of the moving head can be solved analogous to an articulated robot. Then, the moving head kinematic is modeled by using the Dinavitt-Hartenberg convention. Each joint of the kinematic is modeled by a coordinate system, where delta I, I-1 and d, I-1 denote respectively a rotation and translation about Z-I-1 axis. Furthermore, lambda I-1 and L-I-1 represent respectively a rotation and translation about X-I axis. The first two joints are revolute active joints, where the third one is prismatic. The third joint is adjusted passively. The so-called iris value can adjust the scale of the projected area and serves as a value of the third joint. The fourth joint is an active revolute joint and serves to set the orientation of the projected area. This parameter is less important for the calibration and would not be considered in the frame of this work. The coordinate system of the moving head is located on the intersection of the first and second axis, and the z-axis is located along the first rotation axis. The x-axis results from the cross-production of the first and the second axis. The aim of the calibration is to identify the transformation matrix T ward to 0 between the moving head and the ward coordinate system. A methodology is developed at ZEMA for this purpose. 4 points are defined on the ward coordinate system. The points P1 and P2 are lying on the x-axis of the world coordinate system, while P4 lies on the y-axis and P3 lies on the origin. The distances between the points are known. The position of each point P1, P3, and P4 with respect to the moving head coordinate system is calculated after determining the lengths A, B, and F. Due to the inaccuracies in the system, P3 is assumed to lie on the x-axis of the world coordinate system and deviate with small error from its origin. P1 and P4 lies on the x and y axis of the world coordinate system respectively. The z-axis of the world coordinate system, z world to 0, with respect to the moving head coordinate system, is normalized cross product of the vector r P3 to P1 with respect to 0 and r P3 to P4 with respect to 0. The x-axis is then defined as a normalized vector of r P3 to P1 with respect to 0. The y-axis is defined as a cross product between the z and x-axis. The origin of the world coordinate system with respect to the moving head system is then the intersection between the line passing through P1 along r P3 to P1 with respect to 0 and a line passing through P4 along P3 to P4 with respect to 0. The transformation matrix is then calculated. After calibration of the moving head, the latter is able to project any position or any point in the process working space. The coordinates of the projected point are sent to the controller of the moving head via MQTT. The desired configuration of the moving head is determined by solving the inverse kinematic problem of the kinematic model. In the first use case, a typical picking assistance task of manual assembly processes is realized by the ABX, demonstrating the overlapping skills of two devices, the laser projector and the moving head. Manual assembly processes in multivariant production lines can be secured by visual assistance and help to increase product quality. The workspace is described in the following. On the workbench, there are multiple carrier boxes with different parts in them. The carriers can be placed in any desirable position. Augmented reality markers are placed on the corner of the carriers. Each marker contains a part ID that corresponds to the ID of the same part in the MES, which controls the production process. In addition to the projection devices, there is a depth camera mounted over the workspace. The camera is a closed system which is able to communicate via MQTT using the AR markers. The locations of all the carriers on the workbench are detected by the camera and recorded with the corresponding marker's ID. Depending on the process step, the MES sends the ID of the component to be assembled to the camera system. This information is used to identify the carrier with the correct marker ID. The corresponding coordinates are sent from the camera to the ABX using MQTT. The message contains in itself only the coordinates of the carrier. Depending on which projection system is used at the given moment, the process will diverge from this point. The laser projection system projects a line between 2 points on a white stripe at the top of the box to highlight the carrier with the needed parts. The moving head, on the other hand, projects a light beam at the middle of the box. To enable a flexible workspace, the camera updates the coordinates of the carrier in a defined time interval, so that the worker can rearrange the carrier boxes during the process. Another use case is the visual assistance of human-robot cooperation, in which humans and robots work together in a shared workspace. In the build-up demonstrator, the ABX system is used for displaying the individual workspaces of human and robot. In the assembly line, a robot is mounted on the 7th axis and can be moved along the line carrying out assembly processes at predefined different places. In this scenario, two projection systems are needed in order to fulfill the assistance task. With the simple implementation of different projection devices with the help of MQTT and Node-RED, programming effort is reduced while the possible application range is increased, whereby the application in different production environments is ensured. In addition to that, it was shown that the combination of technologies like the Raspberry Pi, a mathematical modeling and calibration, and IoT communication protocols, it's possible to adapt devices from other industries to the requirements of modern production. By doing so, it's possible to decrease processing times because the projection helps the worker to do his task more efficiently and thereby decreasing the probability of errors like picking the wrong parts for the assembly task. The focus of future work will be adding more skills for already usable devices. At the moment, the focus of the ABX was to enable all devices to realize a point projection as a basic feature. A possible extension, for example, for the moving head could be the path projection, which could be used to indicate the path of automated guided vehicles. Another future target is implementing new devices that complement the skill set of the ABX. Thank you for your attention.
Thank you very much, Kanso, for your video presentation. For those of you who has just turned in, we are on live stream to day 2 of the CIRPe Global Web Conference 2019. Our second presenter is from Center for Mechatronics and Automation in Saarbrücken, Germany, and we have him online to answer some questions now. Hi, Ali. Can you hear me?
Hello, Mrs. Speaker. Thank you for your introduction.
Thanks for being with us. I have a few questions to you. First of them, could you give us a bit more information about your structures and projects regarding robotics and automation in your institute?
Okay. Yes, I would like first of all to give a small introduction about my organization and about our research field. We are a research center. Our research field is classified in 3 groups. The first group is the assembly technology. The colleagues there are working with assembly technologies. So they are working with development of assistance systems and planning of modular assembly line in the frame of Industry 4.0. And we have another group. We are working in tolerance management and end-of-line processes in the frame of the mobile industry. And the third group is a group where I'm active right now, and it's a group working with robotics and human-machine interaction. And there we have several projects concerning robotics and robotics applications, and that's why the motivation for us in order to write this paper and to focus on assembly, to focus on assistance system in the frame of human-machine interaction, and also in the frame of only assistant for manual production line or manual assemblies.
Thank you.
Thank you.
In your paper, you have acknowledged one research project funded by the Federal Minister for Economic Affairs and Energy, which is called COMZETSAR. Could you give us a bit more detail about the project and also build a link to your paper and also the relevance for the CIRP community in production engineering?
It's a finance program from the German government in order to help the companies, especially small companies, in order to understand digitalization and in order to have an idea about new technology. factories, in small factories or in small production lines. And so we work there with different partners from the industry and also different research partners in Germany in order to help small companies to digitalize their production lines and always to integrate for assistance system in order to improve the quality. The idea was in a frame of human-robot collaboration, where human and robots will work together in a common workspace. How in order to increase the acceptance of the human that the robot is working right now in front of me. So the idea was to use this assistance system, the moving head, where we have two moving heads there. One can project, for example, a red light, and this can simulate the motion of the robot to the next destination of the robot, and another moving head will project another light, and then another light, for example, can be green light, and then the green light can show the human where he can move right now, what must be his destination. This is in the frame of human-robot collaboration. Another frame is in order to help workers to better understand what they must do right now, and there is a combination between different assistance systems. For example, a laser projector, a moving head, or a projector, or a viewer that we know from presentations, and then it depends on the task. If the task is, for example, to weld a line, so the assist by X system can take a decision. Okay, in order to project a line high accurate, so I need a laser for that. So he takes the laser projection and then he projects a line. This line tell the worker, okay, you must weld right now this line or whatever. And if, for example, if it's about only pick and place, and the human being and the worker must know where he must pick the screw or whatever from box 1 or from box 2 or from box 3. So the boxes so we integrate markers in the boxes. The markers can be measured or can be located with a camera. And the camera is connected via MQTT to our server, and then the location of the box can be sent to our system, and our system takes the decision. Okay, this is we don't need a high accurate assistance system. A moving head is okay for that, and then the moving head will move and project the light on the box where the human being must take the screw or another part. And the moving head, most of the people know the moving head from parties or from theater or something like that. The idea we want to take this moving head, it doesn't cost a lot of money like a laser projector, and we model it like a robot, and we calibrate. Also, we develop a method to calibrate it. So the moving head, we send a coordinate X, Y, and Z to the moving head, and then he can project a point or he can project a circle in the destination.
Thank you for the detailed introduction to your projects. There are also some challenges in working with small and medium-sized companies from the research point of view, but also a lot of advantages for such SMEs. So could you maybe mention some of the biggest challenges you face in several projects, and as well as most of the advantages why the companies are interested in a collaboration with you?
Okay, the idea is with a small company, due to the limitations of the financial part and also of the human part, they are limited in direction, understanding new technology. They don't have sometimes the budget in order to try all new technologies, or they don't have the personnel that can handle with the most newest technology. It's not like by OEMs or big companies, so they have department only for concerning assisted system, or department concerning artificial intelligence or something like that. With a small company, they are more concentrated on their production or on their product, and they cannot collect experience with all over the technologies that are trending right now. So working with us, give them the possibilities and other have an idea about all the technologies that are trending right now in the frame of industrial applications, and then we can help them by understanding these technologies and by integrating what is the integration possibilities of this technologies by their production lines.
Thanks a lot. It sounds like a challenging but also very interesting research field. We are going to follow your contributions in also other conferences and publications. Thank you for your time and hope to see you soon. Bye.
Thank you again.